So welcome back as we continue our study on power series. In this lesson, we're going to focus in on the geometric series. Now, as we talked about in the last section, the power series is sort of like the multi-tool, right? The multi-tool of mathematics. It's like a class of functions, a type of object that can be used to represent a number of different um, mathematical situations and applications. Now, I think about each of these, physical multi-tools that I have in my hand. I think about a wrench, and I'm like, well, what did I do? I've used it for many things over the years, some easier, some harder, but I probably learned it on kind of the basic. Here's the little nut, tighten it up, unscrew it, or tighten it out, tighten it up. I learned about a multi-tool here. I needed to shorten the trim around a door. And so I learned, oh, this is a good tool for plunge cutting, like a very basic application. Since then, I've learned I can use it for a variety of things, but it's actually got a very basic application as a plunge cutter. I think about a cell phone. What did I do first with a cell phone? I probably called my mother, right? So kind of like basic applications. And so just like there are many things that can be done with a cell phone or a multi-tool or a crescent wrench, there's many things that can be done with the power series. But we're going to start by focusing in on the most basic, the simplest application of the power series, namely the geometric series. So this is a specific type of power series, and we're going to learn what it is, and then we're going to learn how much we can get or squeeze out of that one little mathematical uh, um, tool within the power series category. The geometric series. There are infinitely many power series, but some are famous enough to merit a name. The first of these is named the geometric series. The next few examples help us understand this very important but basic example. So we will begin with examples without x and then work our way towards an actual power series, that is, that infinitely long polynomial. Example 2. Evaluate the following. A. The sum from n equals 0 to 5 of 2 times 3 to the n. So let's just understand what we've got here. So we have 2 times 3 to the 0 plus 2 times 3 to the 1 plus 2 times 3 squared plus 2 times 3 cubed plus 2 times 3 to the 4th plus 2 times 3 to the 5th. Okay, this is going to be some number. Maybe I could crunch it really fast on my Texan friend. So I've got, and there's a common factor of 2, so I'll factor that out. So I got 2 times 1 plus 3 plus 9 plus 27 plus 81 plus 243. So I've got 728. In B, I'm going to do something similar, but now I have the sum from n equals 0 to 5 of 2 times a third to the n. So this would be 2 times a third to the 0th power plus 2 times a third to the first plus 2 times a third squared, all the way to ending at 2 times a third to the 5th power. Notice the highest power is showing up there at the end. The lowest power is showing up at the beginning. They won't always match perfectly, as we've seen in our previous examples, but in the cases where you just have a power of n, then they will match perfectly. I guess that n is going to alternate. So the first term matches the lower limit, the last term sort of matches the upper limit. And again, I could evaluate this thing. So this would be 2 times the quantity, 1 plus a third plus a
9th, etc., etc. So I have 2 times 1 plus, I'm going to write it as 3 to the negative 1 plus 3 to the negative 2 plus 3 to the negative 3 plus 3 to the negative 4 plus 3 to the negative 5 and parenthesis. And I've got a number that's just under 3. So this is approximate. So there's all those fractions. Well, I think, let's see if it'll turn it into a fraction. So it's actually 728, interestingly enough, the same numerator over 243, or approximately 2.999. Getting pretty close to 3. Example 3. The upper limit in the sum is important. So the upper limit, that's this number up here. And the sum is important. I want to compare the sum from n equals 0 to 50 of 2 times 3 to the n. Notice that's the same argument inside the sum as in part A before, and the sum from n equals 0 to 50 of 2 times the third to the n. And again, this is the same series as in part B in the prior example, except for in both cases, what's changed is that now we're going to 50 instead of going to 5. And I hope it's clear that when I look at the first one, we're going to go from n equals 0 to 50 of 2 times 3 to the n. You start small, things start small at 2 times 3 to the 0 plus 2 times 3 to the 1 plus, but we're going to go all the way out to 2 times 3 to the 50. Okay. 2 times 3 to the 50, let's see, 2 times 3 to the 50. Oh, this is a really big number. According to my calculator, it's about 1.44 times 10 to the 24th power. That's a heck of a big number. And so what I want to point out here is that when I had this 3 to the n, 3 to the n grows really, really fast. And so since 3 to the n grows really, really fast, you can bet that this sum is going to grow really, really fast. And so it seems to be kind of getting out of control, if you will. A word we use in this class is, we would say that this sum is starting to diverge. It's really wild and crazy. But if we compare that with the sum from n equals 0 to 50 of 2 times 3 to the n, this is the other one, previous example, so 2 times a third to the 0 plus 2 times a third plus plus 2 times a third to the 50. Well, let's see what happens with this last term here. So that last term is very, very small. So 2 times 3 to the negative 50. That term is about equal to 2.79 times 10 to the negative 24th. When you have negative exponents like that, this means this number is approximately equal to 0. And so we can add more and more terms. And yes, we are adding to the total sum, but we are adding a very, 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 very small quantity. Ooh, I have a typo here. I'm sorry. It should be 1/3 to the n. There, my bad. This is adding a very, very small quantity. And so we get kind of this impression that when this number is big, like 3, then this sum goes crazy. Big, like 3, implies crazy. But in the other case, if we look at the 1/3, and if we are small, like a third, well, that means things seem nice. You sort of get this hint. Oh, sorry. Small. Like a third. And that's going to be nice. Okay, so it gives us a little bit of a hint of what's coming. Again, we don't really even know what big and small mean. We don't really know what crazy and nice mean. We need to do a little bit more work in order to truly unpack this. But it does tell us that the 3 seems not promising and the 1/3 seems somewhat promising. So in the last couple of examples, we were letting that upper limit stop at some number like 50. It could have been 500. It could have been 5,000. But what's more interesting is when we allow that upper limit to be infinite. So, oh my gosh, I have so many typos. This is crazy. So instead of having this be an upper limit of 50, what happens if we have an upper limit of infinity? How would that work? Here we got to be a little bit creative, more than a little bit creative. Well, think back to what we did with integrals first. We don't really like to have infinity in the picture. With infinities, we like to kind of incorporate limits. So let's take advantage of just kind of our intuition based on previous things we've done in calculus. And so we could say that the limit from n equals 0 to infinity of 2 times a third to the n would be the same thing as the sum from n equals 0. And now I'm going to go to k. Here I have infinity. Here I have k of 2 times a third to the n. But we want that k to be infinity. And so we'll add a limit as k goes to infinity. Okay, sheesh. Let's see. What does this mean? Now we have a finite sum. So when in doubt, write out your terms and see what happens. So I'm just going to ignore the limit for the moment. I'm going to work for a while just separate from the limit, and then we'll come back to that limit in the end. So this would be equal to, let's see, we have 2 times 1/3 to the 0th power plus 2 times 1/3 to the 1st power plus 2 times 1/3 to the 2nd power, all the way to the last term would be 2 times 1/3 to the kth power. At this stage, we're going to play one of the famous math games. We're going to take this whole quantity and we're going to multiply it by 1. Of course, that's not going to change anything. But we're actually going to multiply it by a special one, like a one that's going to have some cool characteristics. So in order to do that, let's start by taking out the 2. So I have 2. And then 1/3 to the 0 plus 1/3 to the 1 plus 1/3 to the 2 plus dot 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 plus 1/3 to the k. So let's see, what's my special one? So the special one that I'm going to use here is I'm going to use the special one that is made up of 1 minus 1/3 divided by 1 minus 1/3. Now, I think that everyone would agree that this is a 1. You might ask, where the heck did that come from? The ones in the numerator and the denominator will always be the same, but the 1/3 is the same as this common ratio that shows up in the original question. So that's 1 minus the common ratio over 1 minus the common ratio. Okay, let's see what happens. So what I'm going to do next is I'm going to distribute in the numerator. So my denominator is going to stay the same. So I'm going to have 1 minus 1/3. But in the numerator, I'm going to distribute the 1 to each of these terms. All the way through that dot, dot, dot. And of course, there's a 2 that's living on the outside of all this stuff. My line's a little bit long because at some point I'm going to have to come back and add a limit. Okay, so when I multiply by the red, I'm going to get the same thing I started with. So I've got 1/3 to the 0th power plus 1/3 to the 1st power plus 1/3 second power plus dot 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 plus 1/3 to the kth power. Then I need to distribute the 1/3 to each term. So I'm going to come in here, come back here, and now I'm going to distribute the 1/3 to each of these terms in the sum. And so I get negative 1/3 times 1/3 to the 0. So this would be minus 1/3 to the 1. And then 1/3 to the 1/3 times 1/3 to the first would be minus 1/3 squared. And then minus 1/3 cubed minus all the way to the last one is going to be minus 1/3 to the k plus 1. Running out of space. The k plus 1. I want to point out that the green terms are going to the first power, second power, third power, all the way up, and then it'd go to the k minus 1 power, the k power, the k plus power, k plus 1 power. And so there's a whole bunch of terms that are stuck in that dot, dot, dot. And then I hope you could see the really cool thing that's happening. The 1/3 to the first power here and the negative 1/3 to the first power there, those are going to cancel out. The 1/3 to the second power and the negative 1/3 to the second power, those are going to cancel out. All the way to the 1/3 to the kth power is going to match maybe like the last of those dots, so to speak. If there was a 1/3 to the kth power, those are going to cancel out. And you'll notice the only terms that are left are the very first term. Need a new color. The very first term here and the very last term here. So the only ones that are left after all of that simplification. And so we're left with 2 times 1/3 to the 0, that would be 1, minus, I've got 1/3 to the k plus 1, and all this is divided by 1 minus 1/3. Whoa, a whole bunch of that nastiness went away. Now, if we back up a little bit, remember that all this, there was a limit that was out front. So let's go back, now that we've done all this hard work, and add those limits and see what happens. So there's a limit as k goes to infinity. Limit as k goes to infinity, each step. Limit as k goes to infinity. Limit as k goes to infinity. So what is that limit? Well, I think it should be clear that as k goes to infinity, 1/3 of the k plus 1, this is a fraction. So you go, think about those powers, 1/3, 1/9, 1/27, 1/81, 1/243. It should be clear to you that this term here is approaching 0. And so this whole sum is equal to 2 times 1 divided by 1 minus 1/3, that would be 2/3. So that's 2 divided by 2/3. 2 divided by 2/3, or 2 times 3/2 if you invert and multiply, or just 3. Huh. Really close to the thing that we'd found earlier. So we have here evaluated an infinite series. Notice that the 2 that was in the very front here, it hung around all the way to the very end of the question, right? And the 1/3 here also hung around all the way to the end of the question. There's an example of evaluating an infinite series. This is actually a topic that you'll see in the next class, but we're using it because it gives us a pretty direct jumping off point to our power series. So let's reflect on this previous example. So remember that we had the sum from n equals 0 to infinity of 2 times 1/3 to the nth power. Here's the 1/3, here's the 2. And we ended with this formula, 2 times 1 over 1 minus 1/3. So now when we reflect on that, we should see the following pattern. Notice that the a is like our 2, that's the common factor. And the 1/3, well, that would be our x. And so we should be able to see that just by pattern matching, the sum from n equals 0 to infinity of a times x to the n is equal to a over 1 minus x. So in our case, it was 2 divided by 1 minus 1/3. Now, thinking back to the example 2, where I had that common rate, in one case I had a common ratio of 1/3, in another case I had a common ratio of 3, and one of the numbers just blew up, it got really big really fast, and the other got closer and closer to 3. It should be clear that this is not going to be true for all x. So this is going to be only valid for small, whatever small means, x's. So let's keep going forward. So this expression that the sum from n equals 0 to infinity of a x to the n being equal to a over 1 minus x is an example of a power series, and specifically it's a geometric series. It equals a number only for those small values of x. Specifically, in this case, when we say small values of x, we're talking about x values between plus and minus 1, not including -1, not including +1. Why would that be the case? Well, for example, if x equaled +1, this would be like saying, remember, 1 to the 1 is 1, 1 to the second power is 1, 1 to the third power is 1, 1 to the fourth power is 1. And so it would be saying a plus a plus a plus a plus a plus a. Of course, that's not going to equal a single number. So this power series or geometric series is not going to equal a single number when x is either bigger than or equal to 1 or less than or equal to -1. When a series sums to a number, we say, quote, the series converges, end quote. When a series does not converge to a number, we say, quote, the series diverges, end quote. So here's our definition. The geometric series. The geometric series is the sum from n equals 0 to infinity of x to the n. That is, it is 1 plus x squared plus dot 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 plus x to the n plus dot 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 dot. Goes on for an infinite number of terms. And this infinitely long polynomial can be condensed down into this nice, neat formula, 1 over 1 minus x. But that's only true for these small x's, that is, x's between plus and minus 1. So this formula that we found is actually very powerful, even though it only addresses this teeny little instance. So we're able to modify the formula to find power series expansions of other functions. So let me show you an example of that. So example 5, show that the expression 1 over 2 minus x is equal to the power series from n equals 0 to infinity of 1/2 to the n plus 1 over or times x to the n, and this is for absolute value of x less than 2. So let's see how this works. So we're going to start with some rearrangement. So 1 over 2 minus x. Well, let's just factor, this doesn't quite match our formula because our formula would have a 1 in that position. Well, how do we get a 1 there? We could just factor out a 2, which would put the 1 where I want it to be. So yay, I now have a 1. But the problem is when I factored out a 2, I had to pick up this divide by 2 in the x term. And furthermore, this doesn't quite match our formula. Let me make sure you remember the formula we're working on. Recall that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. This is the formula that we just learned earlier. This is what we're referring to. Here's that 1 that we want. But notice there's no 2's in sight. So if we don't like the 2, let's see, we could move that 2 upstairs. So we have a 1/2 divided by 1 minus x over 2. Sheesh. Okay. What I want to point out is this x over 2 really could fit in place of the x in the in the original formula. And so it can go into the power series. Furthermore, we could just multiply the whole thing. Remember, we had that other variant of our formula where there was an A in the numerator, and that's just going to put an A out front in each term of the power series. So this will be equal to the sum from n equals 0 to infinity. And then we have A, which for us is a half. So this half right here. And then I want to multiply by the x, and our x is x over 2, all raised to the nth power, like that. And then we could simplify this. Notice this would be like the sum from n equals 0 to infinity of, it looks like you've got 1/2 times 1/2 to the nth power times x to the nth power. And these two terms can be combined to be n equals 0 to infinity. Oh, let's combine them in red still. To be 1/2 to the n plus 1 power. And then we still have that x to the n power. So this is what we were trying to show with one exception. We still haven't shown how we get the absolute value of x is less than 2. So let's see if we can unpack that a little bit. So recall that in this formula that we're recalling, it's true when -1 is less than x is less than 1, which would be the same thing as saying absolute value is less than 1, of x is less than 1. So it's just sort of two ways of writing the same thing. And in our case, what is that x? So in our case, that x, so this would be when our x, which is x over 2, is less than 1. So here's that green bit. Multiply both sides by 2. You get, or absolute value of x is less than 2. So we took the geometric series formula that we were gifted in the last section, and we modified it to account for the 2, kind of like for the fact that the formula we're working with is a little bit different. So just a little bit of modification, and that geometric series formula could handle things that didn't look exactly like the geometric series formula that we started with. And we're going to do quite a few more examples that will show you time and time again how powerful this simple geometric series formula is, as long as you're clever with your algebra and clever with your calculus. Example 6. Find a power series expansion for f of x equals 1 over 1 plus x squared. When does this series converge? That is equal in number for a given value of x. Now, one thing I'd like to point out is that this function is that we really only have one power function tool so far, namely the geometric series. So if we want to make this thing look like the geometric series, since it's our one tool, let's play as follows. So we can have our f of x, which is 1 over 1 plus x squared. And this will be the same thing as 1 over 1 minus a negative x squared. Okay. So now it's in the form of, so it's in the form of our geometric series, namely the sum from n equals 0 to infinity of a times x to the n equals equals a over 1 minus x. And so here's the x showing up, it's the yellow thing. Here's the a showing up. And so in our case, we recognize that the green thing, the a is going to be 1, and the yellow thing is going to be negative x squared. So this tells us that f of x equals the sum from n equals 0 to infinity of 1, that's our a, times negative x squared to the nth power, which could be written more succinctly as the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n power. And here is, again, our a. Here is our yellow x, or our common ratio. Just a little vocab. This bit right here, that x, or the minus x squared, that's what we call our common ratio. You'll learn about this, the common ratio, a little bit more when you study geometric series in Calculus 4. But for now, we'll just give it a label. So there is example 4. Oh, I'm sorry, we haven't fully answered the question. The second part of the question asks, when does this converge, that is, equal a number for a given value of x? Well, since we use the geometric series, it's going to converge whenever the yellow stuff, the common ratio, this converges when the yellow stuff, namely negative x squared, is less than 1 in absolute value. So you want the absolute value, obviously doesn't care about the negative. So this would be when, same thing as saying when absolute value of x squared is less than 1 and x squared is less than 1 in absolute value when absolute value of x is less than 1. That is between plus and minus 1. So here are the x values on which this power series is a valid expansion for the given function f of x.
So in this lesson, we learned about the geometric series, which is kind of one of the little specific categories of power series. It's like the babiest of the baby first power series that we can learn about. We learned about the relationship between the analytic form, the a over 1 minus x, and the sum from n equals 0 to infinity of ax to the n. We talked very briefly about where this might converge, or its radius of convergence, and where it would diverge. And then right at the end of the lesson, we did some cool manipulations algebraically, where we said, we have this baby geometric series thing, but if we just manipulate other functions, we can take that one little geometric series and we can squeeze a whole bunch more out of it, right? We can take that one thing and make it work for 1 over 2 minus x. We can make it work for 1 over 1 plus x squared. And so we learned how we can use basic algebra in partnership with our formula for the geometric series to develop more power series, like other power series that we can work with. So one little formula actually can be used for quite a bit. And that was our takeaway from this lesson on power series.